Mm-hmm. So today we have a last theoretical lecture in this course. From the next week, we will talk on robot operating system. And today we have the last theoretical block on control algorithms. So we will talk really shortly on control theory, what it is and how it is used, and what are the main terms used in control theory. And then we will discuss three types of regulators which used to control any basically object, but in terms of robotics to control our speed or trajectory. This is PID-regulator, LQR-regulator, and model-predictive control. And then we will see how these things are applied in robotics. So just to remind you where we are here on the control block. We already discussed sensors on the very first lecture. Then we had several lectures on localization, on motion and observation models. We had separate lectures, and on localization algorithms, there was the second lecture in this course. Then we discussed mapping, because map is used in localization and in path planning as well. And the path planning itself we discussed last time. If you have some questions, just don't hesitate to ask. And today we're discussing control. So control algorithms basically take the planned path or planned speed, which we want to travel with, and turn it into control signals, which are then sent to actuators. So this is the last algorithmic block. From the control modules, usually the signal in form of voltage or something else is sent directly to the actuators. So this is the last piece of software, usually in robotics, which is directly connected to our actuators. So trying to describe control theory really shortly. I don't know if you had control courses before, so we will try to start from the very basics. So automatic control theory is a scientific discipline that studies the process of control of various objects. And objects are usually considered as a black box. So for us, it basically doesn't matter what object is, what physical properties it has. We take it as a black box, which converts some input, which we usually send to this black box, to some output signal. So in control theory, we usually do not think on internal representation of the objects we are controlling. For us, they're just black boxes. So the control itself is a purposeful impact on a control object. So we generate some input signals to the object, and we want to have some particular output as a result of our input. And the object, control object, is usually called planned. In control theory, we will use this term throughout the lecture. So the purpose of the control is to ensure the desired operating mode of the plant, so desired output when acting on the input. So our goal, as we already said that output has particular form or level, and for that we are changing input. And control unit or controller or regulator, we will use term regulator, is some software or module or anything or physical device which generates control actions on the plant in accordance with some particular control law. So this thing generates input to our plant in accordance to some control law. And usually as an input of regulator itself, we have control error. So the difference between desired and real level of output of our plant. And the output is the control signal U. So once again, control error is just a difference between required value of the controlled variable and its current value. And we also have disturbance signals. So the control itself, automatic control, would be really, really simple if the world would be perfect and there would be no external disturbances. So sending, for example, voltage to the motor, we would expect the particular number of revolutions of motor shaft, because motor would be perfect, there would be no external forces acting on the motor, and everything would be simple. But we have disturbing signals F, So is the process at the input of the control object which leads to disturbances. I think it may be caused by some external noise. For example, some person just holds the motor shaft, and of course the speed of rotation would be different from one we would expect if there is nobody holding the motor shaft. And also there can be transmission noise of our control signals. Imagine we are sending some voltage to the motor, but on the way in the wires, some part of our voltage just dissipated with heat or something, or we have some short circuiting in our circuit. And then, of course, our control signal will be different on the input of our object from one we are sending. And this is also some kind of disturbances. The output, resulting output, the speed of motor shaft rotation would be different from the expected one. And here's a simple example. This is so-called open loop system. We will discuss in a minute what it is. But for now, imagine we have a car, and we have a gas pedal to control the speed of the car. And this is our system. So regulator in this system is a driver, because there is a driver sitting in the car and he pushes the gas pedal and controls the speed. And our plant or control object is the car itself, because that's the thing we are controlling with pushing the gas pedal. So as an input in this system, input to the regulator, we have a desired speed. So the driver knows the speed he wants to drive. As a result, as the output of our regulator is a fuel supply level. The more we push the gas pedal, the more fuel we supply to our engine. And plant or car transforms fuel supplied to the engine to the speed. And so we are controlling speed in the end by this long process of transmitting the gas pedal, pushing force to fuel supply and to the speed in the end. So why it is called open loop system? Because we don't have any feedback here. Imagine the driver doesn't have a speedometer in this system. So the only thing he sees is the car moving, and he has an internal representation or some model of the car. So he knows that if he pushes the pedal that much, the car would travel with this approximate speed. So there is no real feedback in this system, and everything works just because driver has some internal model of the car inside his head. So he can imagine what would happen if he pushes gas pedal so far. This system works until there are some external disturbances. So as we said, there are some disturbing signal or noise acting on our system. And in this case, we can imagine many such external noises. Imagine we have a wind blowing on the car, and of course our speed would be slower, and the driver, he doesn't know about this wind because he doesn't have any way to measure the wind speed. And that is why he would think that car moves with a proper speed, but in reality it would move much slower because of the wind, or much faster if it blows from the behind. Another example is a road slope. So if you have a even road, of course everything works. But if we have a slope of the road, our previous representation of a car, our internal model of a car, doesn't work anymore, because everything changed, the environment changed, and now we don't know how to act on a gas pedal in order to support the desired speed. And in this case, we use something something called closed loop system to take into account the changing environment or noise, external noise. We add feedback loop to our system, and now we have a speedometer. So now our driver knows how fast he moves just by looking on a speedometer, and this speedometer is the simplest feedback loop. So let's take a look at this more complex scheme. Here we have a desired speed. This circle means addition or subtraction. Black segments mean subtraction, and white ones mean addition. So we have a desired speed minus measured speed. We get a control error. You remember that control error is a difference between something desired and real measured one. So here we get the control error by substituting measured speed from a desired one. And this is an input to our driver. So he knows what the difference between speed he wants to travel and the real speed. And if the real speed is lower than desired one, he pushes on the gas pedal just a bit more. And again, we have a car as our output, we have a speed, but here we have that noise or external disturbances, uneven surface, wind, etc., which is either added or subtracted from our desired speed. In this case, is subtracted because we have a negative slope, so we would move slower than we want to. And it goes with a feedback loop. We measure the resulting speed, and that's the system. So that's the difference between open and closed loop. And we just have a feedback here. So now let's discuss a bit some classical representation, even two representations of systems in a control theory. We will not go into details. This is just for you to know. If you read some book on robotics, on control theory, this is just for you to understand what is written there, basically, and what are the main principles of systems representation. So one of the most common ones is a state space representation. So the state space is a representation of a dynamic system in control theory with two equations, basically. So the first one is derivative from x, where x is our state vector. So in case of a car, state vector could be the position and the velocity, maybe some acceleration. So this is just a vector describing the state of our system. That's why this is called state space representation. And it is just the derivative of our state vector is represented, of course, with our previous state and plus a control we apply to our system. You remember we saw something really close to that when we discussed Kalman filter. In Kalman filter, we also have really similar representation of the system. And then there is a second equation standing for output vector, and output vector, of course, depends on our state and also depends on the control, but with a different coefficient matrices C and D. And all of these matrices have their own names. A is a state matrix because it's in front of our state vector. B is an input matrix, so it shows how our input control signals are translated into state vector changes, and so on. So this is the scheme representing both of these equations. You can see that 1 over s, this is integration. For us, it doesn't matter why it has this form. You just need to know that this is integration. So having derivative of x through the integration, we get x multiplied by a plus control signal multiplied by b, and here we get basically the first equation. And the second one can be restored from this diagram in the same way. You just go over arrows and get those both of those equations. So this is a state space representation. Here is a small example how to obtain it for a real system. Imagine we have a load on a spring, just a typical physical problem. And here is an equation for this system, dynamic equation. So B here is a friction coefficient, K is a spring elasticity, M is a weight of this load. And having this equation, we just can rewrite it with those two equations. So derivative from x1 and x2, where x1 is a position, x2 is a velocity. From the physics, we know equations for such system, and we can rewrite it in a matrix form. And this is exactly what we have here. So our state, which is in this system represented by velocity and acceleration. Our control signals here, which is this U force applied to our load. And the output will be like this. So the output is simple here because we just, as an output, we want to know just x1 and x2, or even x1 actually in this particular example, because x2 is multiplied by 0. So our output is just object position. This is the question we are asked in such problem. So this is just a simple example, and any dynamic system can be rewritten in the form to be represented like this in a state space representation. So, and there is a second way to represent any system in control theory, which is called transfer function. You remember that in a control theory, any object for us is just a black box, and the only thing we want to know is how this black box transforms input signals to output signals. And transfer function, this is exactly the function which shows us this transformation. So U is again input, Y is again output, and transfer function V from S is something, is a fraction of Y, so output over the input. But you can see this S sign here. For now, for us, it doesn't matter what is it. We just will know that this is a Laplace Laplacian transform from Y and from U. So Laplace transform is something really close to Fourier transform. It's just the way to change the basis of our functions to simplify math. And to simplify working with this transfer function, again, here you have seen 1 over S. This is also Laplacian transform from integral, basically. So it doesn't matter for us, at least in this lecture. So we just know that we can perform some transformation over our output and input signal, and then the division of output over input gives us a transfer function in this particular form. And basically, this Laplace transform is just a way to simplify mathematics for us when working with this transfer function. So basically, we change from the time domain, we change to Laplace domain. And then after performing on all mathematical equations, we just change back to the time transform and get an answer. This is how it usually used in real control problems. Just for now, we know that transfer function is a division of output over input. And this transformation gives us a way to represent any system in structural diagrams. You have seen already we used it here, but there are some rules how you read the structural diagrams if you see them in scientific papers or in books. If you have two blocks, one after another, you can just multiply them. And this is exactly what Laplace transform gives us. So in time domain, of course, we cannot just multiply two functions to get the result, but in Laplace domain, we can just simply multiply them and get the resulting transformation of a signal from G to Y. This is just multiplication. If you have these two blocks in parallel, you just sum them up. And this is the really common thing we already have seen with a feedback loop. So the transfer function for such system would be like this, and it has an interesting form. And in numerator, we have just an open loop system, right? So if we won't have any feedback, we just had the system like that, R and P, and we would have multiplication. This is what we have in numerator. And in denominator, we have 1 plus this open loop system multiplied by our feedback loop. And there is an explanation how we get that. You remember the transfer function is something, this division of output signal to input signal. And if we won't have feedback here, this is just RP. And we can represent it in this form. And for new system, we know that input, which was G is an input signal. For the system with feedback loop, G now is G minus Fy, because here we have this minus, this circle stands for minus. So new input, for open loop system, we had input of G. Now we have a new input, G minus F multiplied by Y. And opening these brackets, we get exactly this equation, where in the numerator we have open loop system, and denominator we have 1 plus this equation. So what are the differences, or what are the pros and cons of different control schemes of open loop system and closed loop system? So we have seen that actually in real life we can use both. Just for simple cases, we can use open loop system, and they're really used in some control problems, and they work. For some more complex problems, we could use closed loop system. So we add some sensors to have a feedback loop. So we measure our output somehow, and have this feedback loop. So there are pros and cons of both approaches. For open loop system, they're of course sensitive to parameters changes and sensitive to disturbances. We discussed it. So if any internal or external conditions change, the system becomes unstable because its internal representation of a plant doesn't work anymore. So system becomes just unstable. So if differences expected disturbances are big, we better do not use open loop system. And of course, such system needs a periodic adjustments because environment changes all the time. We cannot assume that environment will be stable for a long period of time. That's why periodically we need to adjust parameters of such system. But there are positive things. For example, such system is really easy to develop, which means it is cheap. We do not use any sensors, any feedback, so it's really easy and cheap. The open loop system doesn't have issues with stability. Of course, it does if disturbances are big, but here it means that with a closed loop system, this feedback loop can lead to instability of systems on itself, and we will discuss it a bit further. So the open loop system doesn't have this problem. And it has a high reaction speed because we don't have to measure anything and run through feedback loop. Here we can react really quick. And if you need a really fast reacting system, usually here open loop system is a better choice. And for closed loop system, of course, it is difficult to develop, expensive because we use some sensor in the feedback loop. We have a potential to stability loss because if this feedback loop is wrongly adjusted, then this system can become unstable on itself. Because, for example, imagine here we have a not a negative but positive feedback, so plus here, and then the input signal is increased all the time, which leads to increasing speed if it is a car and we control speed. And the system will increase the speed all the time and it will lose stability. So if you choose the wrong coefficient for feedback loop, the system can become really unstable. And of course, it is slower because we have to measure something on an input, we have to run it through some feedback, and then on the next loop, we will take some action. Of course, such system is slower to reacting to changing environment. But there are really, really big advantages because it is insensitive to parameter changes, of course, within some certain limits. Because of this feedback, we know that something is changing and we can adjust our behavior to take into account these changes. And it is not sensitive to disturbances, as we said many times already. So moving further, a bit more of theory, we will see what are the types of automatic control systems, because there are many, and I just want you to know what are the categories there are to know what types of the system can be applied and exist. So depending on the degree of human participation, there are manual systems. So people can do take some actions and make some decisions on their own. Then there is a manual control system. So for example, a boat, and your steering wheel is directly connected to your steer. And this is a manual system. There is no automatic, there is no like signal transformation. You just directly turn your rudder on the boat to turn. So this is a purely manual system. There are automatic systems which are purely automatic. There is no human in the loop. The system works on itself, takes decisions on itself. There is no human intervention. And there are automated system, and our example with a car and a driver is actually automated system because human take partial participation in the control loop. So here there is a driver and he makes decisions, but actually between the driver and the engine we are driving, there is a huge signal transformation loop. So as we said, our gas pedal transforms to some electronic signal in the modern cars at least. and then this electronic signal transforms to fuel supply level to our engine, and so on and so forth. So apart from the people, from the person, there is a huge signal transformation path in this system, and that is why it's not purely manual. It is automated. Parts are made by person, parts are made by automatic. So by the signal nature, there are continuous systems which work with a continuous signal. For example, if our fuel can be supplied in continuous manner, meaning any amount of fuel can be supplied to engine, so this is a continuous system. There are discrete systems. For example, if we could supply only like 100, like 1 gram, 2 grams, 3 grams, so this is a discrete system. And there is a third type which is not really common nowadays but still exists. This is a relay type of system. Such types of system means that smooth change in the input signal changes the output abruptly or with steps again. So imagine we could change the force applied to gas pedal really in a smooth manner, as in reality this is a continuous signal, right? And the fuel supply level would change step by step. So this would be a relay system. So there are also linear and nonlinear systems. We also discussed it in Kalman filter section. Linear systems are satisfy this equation. So multiplying input is the same as multiplying output. So the whole transfer function and summing up input signals leads to summing up output signals. So this is the equation linear system should satisfy. And there are non-linear systems. Of course, the majority of methods which are developed work better with linear systems, because that is why we always tried either to linearize our system or to somehow transform it to linear system if we have non-linear. But there are also methods for non-linear systems. They're just much more complex and less developed. And I think the last one, yes, by a control type, we already have seen open loop system, there are closed loop system, and they're also combined. And you can see that open loop systems also can be of two types. So in our example with the driver, we had a system without any information about the plant. So we couldn't measure anything about our car, about our speed. But there are also systems which are open loop. They don't have feedback, but they can measure magnitude of external disturbances. Imagine here we had the sensor which cannot measure the speed, but can measure the road slope. And then we could somehow adjust our internal model of a car, our internal representation which driver has, to try to guess new gas pedal position to maintain the desired speed. So we could measure this. So there are systems which cannot measure the output directly, but can measure these external disturbances applied to the system. And there are also combined systems which both measure feedback as closed loop system and also measure external disturbances. So these are systems which has the maximum of which have maximum of available information. And of course, such systems usually work better. And the last theoretical aspect we have to discuss here is a transition process and its characteristics. So of course, our system, any real system, cannot change its state immediately. So imagine we have again a car, a simple example, and we have a speed equal to 0 here, and then we will immediately want to travel with a speed equal to 1 meter per hour. Of course, we cannot change our speed immediately. It's just physically impossible. And this applies to any physical system. It cannot change its state immediately. And that is why we have something called transition process. So this is a process to system reaction to a change in external condition or to input signal. So we apply new input signal and system needs some time to adjust to it. And this transition process is one of the most important characteristics of any automatic control because usually in a stable and in a steady state, there is nothing interesting happens. If we maintain our speed, we just try to maintain it, and there is nothing special, right? Something and something interesting starts only when something changes, either external disturbances, or we want to travel with a new speed and we change our input signal. So this transition process is characterized with many characteristics, but there are some just the most important ones I want you to know. So there is transition time, is the time during which the output signal approaches the steady state value with some delta. And steady state value is either value on the infinity in theory. So we have this transition process, and it will last forever. In the infinity, we have some signal level, and this is steady state. But in reality, in practice, of course, it is not an infinity. It's just some stable value we get after the transition process. So here we could see that system approaches desired one, let's say, meter per hour already in 10 seconds, and we can call this as steady state. And so transition time is the time we reach this steady state. Then there is a really important overshoot characteristic. So it is basically how much we overshoot our desired value. So here you can see that our desired value is 1, but we reach almost 1.2. And why this characteristic is important? Because in a real physical system, it would mean that we work on some unusual level of signal. Imagine we have a steering wheel in our car, and we want to turn it on a maximum angle, but with our control system here, we would turn it a bit more than a maximum angle. And in practice, it means that we would really apply huge force to our steering wheel, pushing it forward after the maximum turning. And of course, it can lead to physical destruction of the system. So sometimes this overshoot can lead to physical destruction of our motor, of our steering wheel, or any object we are controlling. This is why this is a really dangerous to overshoot, and we usually in practice we try not to overshoot. But usually there is a trade-off between overshooting and transition time. So we want to reach our desired state, our desired signal level as fast as possible, and usually it leads to bigger overshoot. So there is a trade-off. Also, there is oscillation. This is a modulus or absolute value of the ratio of the amplitude of the first and second oscillation. So here we have the first oscillation, here we have the second. So the absolute value of the ratio is oscillation, and of course we want as small oscillation as possible, because the same reason as overshoot, we don't want to oscillate a lot, we just want to reach our desired value. And there is a steady state error, so some systems are unable to reach desired value even in infinite time, and there is small error even through really huge amount of time, which is called steady state error. So this is a difference between the desired and real value of output signal at the infinity. There is another picture showing the same thing. So there is overshoot. You can see that desired value is in green. There is a big overshoot first, then there is a big oscillation, and in the end we reach some steady state value, but we can see that there is steady state error, because even on the infinity we still have difference between desired level and our real level. So these are the main characteristics of the transition process. And also the last thing, 3 types of system we can distinguish. There is a stable system. So our after transition process, this system slowly reaches the desired level, or quickly reaches the desired level. So the main thing here is that oscillation is decreasing and we reach the desired state. Also, there are unstable systems. So for these systems, oscillation is increasing, and usually in the end, this just leads to physical destruction of the system. So for example, with a simple electric motor, we can get this type of system if we control it incorrectly. and it really leads to the physical destruction of the motor. So if our control law or our regulator works improperly, it can lead to such unstable output signal. And there are also systems at the stability boundary. You can see that in such systems, oscillations do not become bigger, so there is no growing oscillation amplitude, but they also do not become smaller, so we are not reaching a stable state. And there are real systems working on this stability boundary. Sometimes it's just needed in our control problems. And again, any electric motor can be pushed to this state. So if you control it incorrectly, you will have, for example, if you control the desired shaft position of the motor and you overshoot it, and then you try to correct and overshoot it back, and then you try to correct again and overshoot it front. So the simple electric motor can have this state on the stability boundary. So all three types can be reached with a single control object, just depending on the control algorithm or regulator you apply. And of course, usually we aim for stable systems. Usually in classical control problems, we just try to make transition process as quick as possible and to reach our desired level as quick as possible with small oscillations and with small overshooting. So, and now we will discuss three types of regulators, and we will start with PID-regulators. This is the simplest and the most common regulator, I think, in any control problems. Usually people start solving any control problem by applying PID-regulator and see if it works. So how it works? Again, this diagram is quite familiar to us already. So we have our plant or our controlling process. Let's again, as an example, use a car and the speed. Imagine we have a car, we try to control speed. As an output, we have y, which is speed of the car. We have a feedback loop. Here we have a subtraction of our desired speed and real speed. We get an error, E, here. And here are three blocks our error is applied to, and then we have a summation of these three blocks. And PID-regulator stands for proportional integral derivative regulator. There are some formal equations for a continuous case and for discrete case. For us, it doesn't matter right now. So we will start discussing PID-regulator from proportional component. So this component is proportional to error, and you can see that we just multiply our error to some coefficient, Kp. So this is called P-regulator. The output is proportional to the deviation of the output signal from a set value, so to our control error. Of course, if the input signal is exactly equal to our set value, to our desired value, then the output is equal to 0. So if error E is equal to 0, because the desired and the real velocities are equal, the whole block will be equal to 0, because multiplying anything to 0 will get 0. But due to the static or steady state error, we said that any system has, almost any system has steady state error. The output of proportional controller never stabilizes at the set point. So with a pure proportional controller, so imagine we don't have integral and derivative part, we will never stabilize to our desired level, because there are external disturbances which will lead to either overshooting or undershooting the desired level. That is why we usually cannot apply pure proportional coefficient. So in the example here is with kettle. So imagine we have a heater inside, and it cannot reach the set or desired temperature, because in this case the air and the power of the heater will become equal to 0, and it will lead to the kettle to start to cool down. And once it cools down, the error increases, and we again apply some signal, and this is an infinite thing. So once the proportional component is equal to 0, the kettle become to cool down. And once it becomes to cool down, our error increases, and we have to switch on the heater once again. And this is an infinite thing, and that is why it will stabilize somewhere, but not on the desired level. So we will never reach the desired temperature. We will be somewhere really close, but because of this infinite oscillation, we will never reach it. And the large proportional coefficient usually leads to smaller static error. However, if it is too large, self-oscillations may begin in the system, as we discussed in the case of this kettle. And with the further increase in the coefficient, the system may become just unstable. So you can see here on the video that by increasing proportional coefficient, we increase the reaction time of the system. So our reaction becomes faster. You can see that with proportional, we reach the desired state, but once increasing it too much, we get these oscillations, and we still never reach the desired state because of these oscillations. So also there is integral component, the second one, and you can see that here we multiply some coefficient to the integral of error. So we integrate an error over time, and multiply some fixed number, some coefficient to this integral. And what it gives us is that it allows us to take into account this steady state error. So if we have this steady state error, our integral component will become bigger and bigger over time because we're just summing up an error. And in the end, we will reach the desired state because integral component will become bigger and bigger. And it will allow us to neglect this steady state error. So this component allows us to fight this steady state just by integration. And the third one is derivative or differential component. And this is proportional to the rate of change of the control signal. So once we are changing our control too quick, the differential component becomes big. And it kind of stops or slows down changes in the system. So the derivative will be negative if we change our control signal too fast, and it will allow us to slow down. So this component kind of looking into the future and trying to prevent too quick changes in the system. And this is something which allows us to fight this overshooting usually, because with the quick changes, we have the big overshooting, and you can see that by increasing derivative, it just prevents us to change the signal really quick. Yeah. So it is designed to counteract future deviations from the set value, because by counting differential or derivative, we can react to the speed of change, not to the change itself. As with integral or proportional regulator, with derivative one, we can react to the changes of the signal. So basically, this is how PID regulator works. We have a sum of these three. All of the components are trying to solve some issues. So proportional is responsible for the majority of the signal. It just allows us to really quickly react to the error just by multiplying it to some gain. The integral part works to neglect the steady state error because it integrates error over time, and even if the error is small, we still will integrate it, and this time we will correct it with integral coefficient. And derivative part allow us to react to the speed of change of our signal, and this one is usually used to slow down this change and to overcome overshooting in the system, overshooting and oscillation, because without derivative part we can have these huge oscillations. With derivative part, it will just slow down this change of the signal and will stop us from overshooting the desired value. And you can see here example of coefficients for some particular system. For different systems, these numbers will be really different, and this is the whole science behind how we choose these coefficients, and we'll discuss it in a minute. But the main thing here is that by using all three, we can get the transition process which is really smooth and which reaches the desired value really quick. So, and for tuning PID regulator or for choosing these coefficients, there are many methods. There are manual methods, so we can just see on the output and manually adjust these coefficients. There are heuristic-based and optimization-based methods. For example, we can compute an error, like integral from the error for the whole transition process, and then we can, with some optimization method, change these coefficients by trying to minimize this error. This also works. But unfortunately, all these methods, which assume that you have a real system and you can measure the real output, they don't work for really complex or expensive systems. So imagine with a PID regulator, we are controlling car speed. And of course, we don't want to run these experiments setting up these coefficients with a real car, because it's just expensive. We can break things down. You remember that with a huge overshooting, we just can break our motor. And that is why these methods should be applied to some model of an object, because if applying to real object, trying to play with this coefficient can lead to destruction of the system. So yeah, and there are also online methods and offline methods. For example, optimization. If we have our model of our system, we can run offline optimization, just optimize, find some coefficients, and then apply them to our car. And there are online methods when, while running the objects, we try to change these coefficients to reach some desired state in online. So we can try to see that something changes in our system and to find new coefficients just while working. But these are really usually complex methods, and they're not always used in practice. In practice, we usually have a model of our system. We try manually or with optimization, find the suitable coefficients which make our transition process smooth and quick, and then we apply it to the system working in online. So this is regarding PID regulator. Maybe you have some questions here. So the second type of regulator is LQR, or linear quadratic regulator. This is an optimal regulator. So in case of PID regulator, nobody promises us optimality. So we just choose some coefficients and try to see if transition process is good and suitable for us. And that's it. Here we have an optimal regulator, and optimal control is a control that provides for a given control object and control law that is maximum or minimum of a given quality function. And in the case of linear quadratic regulator, we have a quadratic quality function, and we will see in a minute what it is. Here are some equations. You can see a state space representation of the system for continuous and for discrete case. And G is a quality functional. It has a scary look, because here we have an integral or summation, and we have some scary multiplication or squaring here. We'll see in a minute that this is quite a simple thing, a simple idea behind. So this quality functional J is a sum or integral for a continuous case, doesn't matter, over the infinity. You can see that this is a sum over the infinity of two simple things. So first one is a penalty for the failure of the system to achieve the desired state. So Q is a matrix where for each element in our state vector, so X is a state vector. So for example, in terms of car, it could be position and velocity and acceleration. So we multiply our state vector to the special matrix Q, which holds the penalty for each state member for not reaching desired state. And we have a square here just because the deviations to negative direction are not subtracted by added to the penalty. So for us, doesn't matter if we move slower or faster than we want, it both should be penalized. So this term works really simple. Imagine we have a desired velocity and we have a real velocity, and we just square the difference. So we square the error and multiply to some number written in matrix Q, depending on how much we should penalize our car for reaching too fast or too slow. For example, there are problems where speed is more important than the position. So we care about car speed more than about actual position in the world. And in this case, in the matrix Q, there will be a bigger penalty for deviation from the desired speed than from deviation from the desired position. So this matrix just allows us to penalize different parts of our state vector with different penalties. And the same with the control signal. Imagine we have limited control. This is a good explained with, for example, space shuttle. A space shuttle has limited amount of fuel, and we don't want to run out of fuel. And that is why any control action taken with a space shuttle, any control action uses some fuel. And of course, we don't want it. We want to use as less fuel as possible. And this second term penalizes our control actions, basically. So we know that we don't want to use fuel. That is why any changes in our speed would be penalized with a number written in matrix R. Or, for example, we don't want to steer a wheel a lot because this is just uncomfortable for our passengers, and our matrix R would penalize steering. If we steer too much, we will get a big penalty. So these are two members of this equation. One is penalizes us if we are not reaching the desired state, and the second one penalizes us if we are controlling too much, steering the wheel too much, or using too much fuel, or speeding up, slowing down too much. And by using both of these terms and by summing them up over the infinity, we get our quality functional. And of course, we want to minimize it. And there is mathematical theory how we get the control law that minimizes this quality functional. For us, it doesn't matter at the moment. So you can see it on Wikipedia or in control theory book, how to get the function which minimizes it, but here it is written. So our U, which is control for continuous and for discrete case, are well known. So to minimize such quality functional, we just need to apply control law, which is like this. So there is a special matrix F multiplied by our state. And this is how we get optimal control law. So you just can read it in a book. If you have a system and you have such a quality functional, you can just find it how to control the system to minimize this quality metric. And this is really cool because this guarantees us that we are not too much from the desired state because we are penalized for it, and we are not using too much resources. Any resources we could think of, we can put in this matrix. So, and here's just a simple example. Imagine we want to eat pizza and we have our resource, which is time, and we have a taste, which of course we want to be as tasty as possible. And this is the first term, and our time is the second term here, right? And of course, we can cook it on our own. We can just order delivery. We can fly to Italy to eat pizza. And all of this would be a trade-off between spending too much resources and between obtaining the better pizza we want. And this is what this linear quadratic regulator does. It finds trade-off between the desired state and spending too much resources on it. And this is a really good and really widely used control law. So it can be used in the same problems where we use PID-regulator. For example, we want to control speed. Of course, we want our speed difference or our speed error be as less as possible. But we also sometimes, for some problems, don't want to accelerate too much. And this is, for example, for autonomous cars, this is really important because if you have people on board, accelerating really quickly will be just really uncomfortable for people on board. And this is why we can use this second term to control our acceleration. We never want to accelerate immediately with a huge acceleration. And this control algorithm allows us to take into account both of this. So, and there is the last thing, the third one, called model-predictive control. It is in the idea quite similar to linear quadratic regulator, you have to understand that model predictive control is not a particular algorithm. This is the whole family of algorithms using the same idea. So idea here is the following. We're optimizing our control on a finite planning horizon. So if here we had an infinity, here we have a finite planning horizon. We use our system model. So we have some model of the control object. And we use optimization to optimize our output. So imagine we can predict what would happen with our system, which if we generate some input. So for example, we have a car and we know that we generate some input to our speed. Our system would behave with the following way. The speed would change. It would change that much because we know the model. And we can optimize here. So we can have a finite planning horizon, for example, 10 seconds. And we can optimize our behavior having our system model. So we can predict what our system would do if we apply that much acceleration or something. And of course, there is optimization criteria coming inside. And optimization criteria can be the following as here, and it is actually widely used. But we can use any optimization criteria. For example, for us, only matters how fast we would reach the desired speed, and acceleration that doesn't matter. So that could be an optimization criteria. And the cool thing about this approach that it can also take into consideration some limits. So here we just have infinite planning horizon, and imagine if we could, if something changes in between, we already planned everything because we optimized our control function on infinite planning horizon. We are not changing anything even though if environment changes. So for example, if we see an obstacle on the road and we control the steering wheel, we cannot change anything because we already optimized it for the whole journey. Of course, we can recompute the whole thing, and usually that's what people do, but this is impractical because we first planned everything in advance for the whole journey of our car, and now we have to replan again for the whole journey. This is not really cool. And for model predictive control, we have a finite planning horizon, and that's something that allows us to take some new appearing limits or environmental changes into account really quickly. So yeah, and the important thing is that by design, we re-optimize the whole thing on each step. So imagine here we have a prediction horizon, and here in this example we are controlling the trajectory of our car. So we have a reference trajectory in red. This is the trajectory we would like to follow, and we have a predicted output. So with our we are here at the point K. We have measured output. This is our past. This is something we already traveled. And we have to, at this step, to optimize our control algorithm for the future. So we can predict, this is a brown line, we are predicting that our car will move like that. And to move like that, we need our control input like this, the green one. So this is just a control to our steering wheel, for example. So this is a control signal we need to apply to our steering wheel to get the path like this in brown to reach our reference trajectory as quick as we can. But then after this, so we planned everything on a step K, we would move one step further to step K plus 1, and we will optimize it from the beginning. So from this point, we will optimize the following trajectory again for the whole prediction horizon. So prediction horizon will stay the same. It is constant. It is K plus P. It is P steps ahead. But we will move this prediction horizon one step further and then replan the whole thing again. And this will allow us to take into account everything which changes in the future. So we don't have a single control law which is unchangeable and we have to follow it. We change our control law every step and we optimize the whole system from the beginning. Of course, it is computationally expensive. That is why on simple robots, usually people do not use model predictive control because we will have to need the whole system model, and we will need to run this modeling and optimization every time step from the beginning for our finite planning horizon. Our finite planning horizon can be small, for example, like 2 seconds in the future, but still this is an infinite loop, and we will have to run complex kinematic or dynamic equations to model our system and to optimize our input to reach the desired output. So that is why this thing is usually used on the complex robots, on autonomous cars. For example, this is used a lot to control the trajectory, as in our example. But the cool thing here is that model predictive control, or MPC, it is able to accommodate the constraints on the external environment. So for example, here we can have a speed limit, and our optimization loop knows that it cannot run faster than 50 kilometers per hour, for example. Here in this approach, or in PID-regulator, it is much more complex to inject such limits, because there is no mathematical way for us to have these limits. For example, for PID-regulator, of course, we can, if our system or PID-regulator gives us a speed of 1.5, of course, we can say that no, it still should be 1. But that makes the work of PID-regulator not effective. And we have to take additional actions to prevent the system from speeding up too much, for example. And here in MPC, we can know or accommodate future events directly in our control law. For example, if we know that there is a turn somewhere in the future because we have a map, we can directly use it here because we have a planning horizon, and we know that at some point of time we will need to turn, and we're directly accommodating in our control law. Imagine with PID-regulator, imagine a PID-regulator controlling a steering wheel. So the signal would change only here. So we will get our steering wheel straight until the exact turn happens. So until we need to turn it already. So as we discussed, as you remember, our transition process will start only here. And that is why it will be really, really sharp. So from 0 angle to 90 degrees angle, we will need to turn our steering wheel really sharp. So as here, our control signal will change from 0 to 90, and our steering wheel, with the control law, with PID-regulator, we will try to steer it as quick as possible. And of course, it will be uncomfortable. And the thing is, we knew in advance that there is a turn. But with the PID-regulator, we just cannot use this information anyhow. And with model predictive control, since we are predicting in the future, we can take this information from the future into account. And that is why this is really wide common technique to use. But of course, particular algorithms, as we said, this is a family of algorithms. Particular algorithms can work in a different way inside, and this optimization criteria, it can be linear quadratic optimization or any other way of optimization. So this is just a general idea for understanding how model predictive control works. So, and the last thing, I hope you realized it throughout the lecture, but what are usually these algorithms are used for in robotics, in a wheeled robotics, since we are discussing wheeled robots. So there are two main problems in a wheeled robotics. Usually we control just two things. We control speed, and for this, a simple PID controller is a perfect choice because speed changes like with the steps usually. And that is why PID controller can be used to control the speed. And we also control trajectory, as in this example, we have some reference trajectory generated by our path planner usually. And control algorithm just tries to stay as close to this planned trajectory as possible. And usually here we have a so-called cross-track error. This is a difference between perpendiculars to closest points of two trajectories, and we try to minimize this cross-track error usually by controlling trajectory. So this is the main two problems in wheeled robotics. And there is a really good paper I wanted to discuss with you really shortly, if my laptop works properly. Let's try. So this is a really famous paper from Stanley. Maybe you remember that Stanley is the robot which won DARPA Grand Challenge. Okay, let me just find it in Scholar. So in 2005, DARPA, or American military agency, organized the competition of autonomous cars. That was the first autonomous cars competition in the world. And there was a team from Stanford which built this robot called Stanley. And they actually were, in the first year, in 2004, in the first competition, nobody won because not a single team reached the finish line. But through the year, in 2005, there was many teams already who was able to travel through the desert on autonomous cars. There was a test track like this, and the Stanley was the winner, and it became really famous. And the Stanford team is still working on autonomous cars. They have really good ideas, papers, and actually the team leader of this Stanley team is Sebastian Thrun, which is wrote the book on probabilistic robotics, which we have on Piazza. This is the main book on probabilistic robotics. So he is a father of the discipline, and now he's not already, but like 5 years ago, he was leading a Google autonomous cars programs. So he made a lot in the area of autonomous robotics, and this is a really good paper on Stanley. So they describe how their robot was working for this competition. And there is a small part, you remember maybe on the first lecture, we have seen this diagram, and you can see that this is close what we are discussing. So there are sensors, perception, and unsended Kalman filter pose estimation, which you already know what is it, planning, and there are control. And you can see that there are two control algorithms, steering control and throttle brake control. So as we said, in wheeled robotics, we usually controlling two things: steering or trajectory, and speed with a throttle or brake. So there is a section on how their control algorithms was working at that time. It was quite simple, but it's still widely used. Let's just see how it was working. So as we said, there it is, a section on steering control. So there is a two errors we try to minimize. One is called cross-track error, is X. So the difference between our car and the closest reference trajectory segment is called cross-track error. And of course, we want it to be as small as possible. Also, we want our car to be as parallel to our reference trajectory as possible. So of course, if the reference trajectory goes like that, we want our car to be parallel to it. So by minimizing both of these things, to be parallel to the line and to be as close to the line as possible, we would travel through the desired trajectory if both of these errors are zero. So if we are close to the line and we are parallel to the line. And then they came up with a really simple steering control algorithm. Where it is. So this is the control law they used. So, okay, I have my laptop dying, so sorry for that. So basically, they had a proportional control. You can see that K is a gain parameter, and X is a cross-track error. So basically, the bigger the cross-track error, the bigger is the arctangents is, and phi is a steering angle. So the bigger the cross-track error, the faster we try to steer our wheel to turn to the desired trajectory. But there is a u in the denominator with this speed. So basically, the higher speed we have, the slower our turning would be. And this is practical. So just imagine the car moving really quickly. And if we turn our wheels or steer our wheels really fast on a huge speed, this is just dangerous, and we will break something on our car, or even something bad really can happen. So with a bigger speed, we don't want to steer our wheels really quick. So, and this is it. Basically, This is not even a PID-regulator. This is something way simpler. So we have our our steering plus the steering due to the cross-track error. So further away we are from our reference trajectory, the faster we are trying to return to this reference trajectory. But with a bigger speed, we are trying to not to steer too quick. And this is one of the simplest control algorithms for steering, for controlling the trajectory, but it really works. And our tangents here is just to switch from some numbers to angles, so obviously from -pi to pi, because we're in the end, we want to get the steering angle of our wheels here. So we need to work with angles in the end. And there is some justification that this control algorithm is working. So they're proving that this control algorithm is stable. It will never lead to instability in the system. You remember that instability is when we try to oscillate, for example, our steering wheel or something. So there is a mathematical proof, but the whole algorithm is really simple. After that, in a year, they came up with a more complex algorithm here, but that was the first one. It works and it's still applicable in many cases. So simple robots usually use this algorithm. So once again, there is this angle, which is orientation of the nearest pass segment. So we at least want our wheels to be parallel to the closest line segment, and this is it. But also we want to minimize the cross-track error, because that is why we have additional term here, which depends on cross-track error. And we just transform our cross-track error, which is in meters, to angles with arctangents. That is it. That is quite simple. So that's it for today. I hope you get some sense of control. I really suggest you to see this first video. This is the best explanation of PID regulator I know, the simplest one, and it is also from one of the teams which participated in this DARPA challenge. They also built the autonomous car, and in this video they just try to explain how PID regulator works in terms of controlling the trajectory. So I really suggest you to watch this video. It's just 4 minutes long, but it gives you the whole understanding of PID regulator. And there are also videos on linear quadratic regulator and model predictive control. There is also a link to this paper, Stanley. Read it if you are interested. This is a really good explanation on how the whole autonomous car works. So they run through the different systems they developed and describe how each system was working. And since it was like 15 years ago, the whole system was much simpler than modern autonomous cars. So it is really simple for understanding and give you a sense of what problems are usually faced when you're building autonomous robots or self-driving car. So that's it for today. Do you have any questions?